A lonely star is just like a lonely person. However, when they pair up, their lives are filled with events. Stars, by exchanging mass, can make evolution, become variable stars, and produce bright X-ray sources. But occasionally, there are far more epic cataclysms, when the stars merge in a final, deadly embrace. Yeah, the single stars can only dream about something similar. Binary star, a system of two stars, occur quite often. In fact, the massive stars have a better chance of finding a neighbor. More than half of the massive stars exist in pairs. But among the low-mass stars, about a third of them are also binary star. In general, stars are gravitationally bound from the first day of existence. Gravitational captures sometimes occur only in dense clusters. This requires that three stars must come close together, and then, with a lucky coincidence, two of them will orbit around each other in a closed orbit, and the third will fly away, taking away the excess kinetic energy. Or the two stars must come very close to each other so that due to the colossal gravitational tides, they will get rid of the excess energy and angular momentum that prevent them from becoming a pair. Even if the stars were born as a pair, they don't necessarily have to be twins. The mass, which plays a crucial role in the fate of a star, can vary greatly among the components of a contact binary. Stars are fairly simple objects. Usually for a medium-aged star, knowing the mass is enough to determine all the other parameters, such as luminosity, size, and temperature. For example, 1/5 of a solar mass star will be a faint red dwarf. So, a binary star of different masses can sometimes look very beautiful. For example, at Albireo or Beta Cygni, one component of the system is orange, and the other is blue. However, the stars that compose the Albireo system appear to be twins only at first glance. On closer observation, they turn out to be triplets. The brighter orange star is in fact a binary itself, but this can only be seen with large telescopes. There are systems of not only 3, but 4, 5, 6, and even 7 stars. Although, their components still tend to split into pairs. Such binary space arrangements are not coincidental. They allow the stellar system to exist for a long time. Even if we try to create a triple star system, in which all the bodies are approximately equal distances from the common center of mass and orbit around it along intricate trajectories, such a process will soon be interrupted. One of the stars will be permanently thrown out of the system. The only reliable way to achieve stability for a multiple star system, for example, consisting of 3 or more stars, is to create it hierarchically. But this way, not all the stars will be able to interact and influence the evolution of their nearest neighbors. Only those at the very bottom of the hierarchy will be able to do so. The distances between the other components of the system are so long that they have no noticeable effect on each other, and they will evolve as single stars. For astrophysicists, the most interesting are close binaries. First, their interaction can change the mass of stars, the main determinant of their properties. Second, in the process of mass exchange, unusual bright sources of radiation can arise, which makes the life of the star more diverse and fascinating to study. Let's imagine two close stars, mentally draw a line connecting them, and calculate where the center of mass of the system is located. If we put a stone in it exactly, it will stay there. The gravitational forces from the two stars will be exactly balanced. If we move it toward one of the stars, it will orbit around it. In other words, each of the pair's components is surrounded by its sphere of influence, and the center of mass is the critical point, which is called the inner Lagrange point. The material in such a region orbits around one of the stars of the pair, that is, it is controlled by its gravitational field. Usually, stars are deep inside their Roche lobes, areas dominated by the gravity of one of the components of the binary system. Each of them securely holds its material, preventing it from leaving the surface. As long as this state of the system remains, the stars evolve as single stars. But in the later stages of existence, when the star becomes a red giant, its size increases by hundreds of times. As a result, there is a risk that it will be unable to fit into its Roche lobe, and then its material will begin to flow to the other star, so a contact binary appears. In a binary system, the more massive star is the first to reach the red giant stage. Therefore, the greater mass provokes faster evolution. However, at the beginning of the interaction, the smaller star of the pair begins to increase its mass at the expense of its neighbor. Thus, those stars that seem destined to become white dwarfs may end their days as neutron stars or even black holes. On the other hand, rapidly aging massive stars may transfer some of their material to a neighbor with less mass and look younger after that. This is how the Algol paradox can be explained. This binary star in the constellation Perseus, the less massive component, is at a later stage of evolution than the more massive one. Finally, the stars may even merge with each other. As a rule, if stars began to exchange material, it is not limited to a one-time action. Let's take two stars with masses of 12 and 9 solar, which orbit approximately 2.5 times the Earth's orbit around the Sun. The more massive star is the first to fill its Roche lobe, and its material begins to flow to its neighbor through the inner Lagrange point. In addition, some material is dispersed around the system and does not participate in its further evolution. When the matter exchange is completed, the first star is almost 4 times lighter, and the second is slightly heavier. In addition, the system has become much more compact and lighter due to the loss of material. After a few million years, the component, which was initially more massive, explodes as a supernova, turning into a neutron star. But this does not mean that its fate is now finally determined because it is in a close binary system. After a while, it is the turn of the second star to become a red giant. It, too, fills its Roche lobe, and its material begins to flow to the neutron star. During this process, it heats up to millions of degrees and a bright X-ray source lights up in the galaxy. While the overflow occurs, the orbit of the binary decreases in size. First, part of the energy of the star's orbital motion is carried away by the material leaving the system. Secondly, the alignment of the masses of the components leads to this. If we transfer a bit of its material to its faster-moving neighbor, it will slow down a little, and therefore come closer to the center of the masses. Decreasing orbit leads to catastrophic consequences for the system. A neutron star may fall inside a giant star and form the so-called Thorne-Zeitkow object. A single black hole is the final result of the evolution of the system. Although, separately, the single stars of the original pair could not have produced such a compact object. If we take the mass of the second smaller star, for instance, not 9, but 2 solar masses, leaving all other parameters unchanged, the fate of the system will be quite different. There will be no star merger in it. Instead, there will be several stages of material exchange, and a bright X-ray source will appear. Again, the second star will flow into the neutron star formed from the first one. But in the end, there won't be a black hole, but a pair of neutron star and a white dwarf. We can change the variables just a little bit more and again get noticeable differences in evolution. Thus, there is a huge variety of close binaries. Of all the phenomena of close binaries, perhaps, X-ray binaries are the best known ones. This stage occurs during the existence of many contact binaries, when one component of the system, becoming a neutron star or black hole, captures, or, as astronomers say, accretes, the matter of its neighbor. Accretion is a surprisingly efficient process for generating energy. If you take a brick and throw it at a neutron star, the impact on the surface will release as much energy as a powerful nuclear warhead exploding. Astrophysics stands out among the natural sciences in that it is impossible to experiment with the objects it studies. Therefore, researchers are happy to use any version of natural sensors. For example, if eclipses occur in the system during orbit when one star obscures another, it is possible to get an accurate estimate of their size. Nowadays, experts can easily say, the more massive the star, the more. However, some time ago, Measuring the stars' masses seemed like science fiction. And yes, how is it even possible to weigh a lonely gas ball flying in the void? It is a different matter if another object orbits around it under the action of gravity. In this case, by measuring the orbital period and velocities of stars in the binary system, it is possible to estimate their masses according to the laws of celestial mechanics. Just like almost everything in the universe, binary star collapse. There are two reasons for this. The first one is because of the villain star, whose close passing by the pair may lead to an exchange of partners. The second reason is that one of the stars may explode as a supernova. In this case, a significant amount of its mass is ejected into the surrounding space. The pair is held together by the mutual force of gravity. If more than half of the total mass is ejected, the system becomes gravitationally unbound, and the stars fly apart. In addition, supernova explosions are asymmetric. As a result, the resulting compact object receives a jolt at the moment of explosion, an additional velocity. If it is too large compared to the orbital velocity in a contact binary, it also leads to the breaking of the stellar pair. Therefore, although more than half of the massive stars, which then produce neutron stars or black holes, are included in contact binary, the fraction of binary among compact objects is much smaller. For astronomers and physicists, contact binaries are of great interest. Such paired dances and the complex relationships between them make it much easier for us to explore outer space.